expanding the binomials. If we've got 1 plus x to the power of n, we could expand the whole thing out the long way if we really wanted to, which of course we don't, because now we know we could use Pascal's triangle. But let's think about what we actually do when we expand parentheses. What we're really doing is taking one term from each set of parentheses and then multiplying them together. So, for example, one way I could get an x cubed term is to get an x from the first one, then a 1, then an x, then a 1, then a 1, then a 1, then a however many I've got there, and then in the last one get an x, and I would end up with x cubed. But that's only one way of doing that. How many different ways could I end up with x cubed is the question. And this then, in a really nice, let's tie everything up into a nice neat bow. In our final topic of extension 1 brings us back to our first topic in extension 1. What we're really saying is how many different ways could I choose 3 x's from n sets of parentheses? NC3. It's back to combinations again. So the answer is NC3. So basically, we could do that for any of the terms. General expansion of a binomial. NCK will always be the coefficient of x to the power of k in 1 plus x to the power of k. So that C, which before we said stood for combination, and it still does, could also mean coefficient. How cool is that? Sometimes in binomial theorem, though, we write it a different way. We write it in parentheses like this. Now, it's not a fraction. There's no vinculum there. Right? So it's just n on k. Vinculum's fancy name for fraction bar in case those are going, vinculum? What's vinculum? Okay. So the full expansion then of 1 plus x to the power of n would be nc0, nc1x, nc2x squared, and so on and so on and so on, up to ncn x to the power of n. That's for 1 plus x, but of course there's no reason why we couldn't do it for anything. So a plus b to the power of n, the only difference is the powers of a go down by 1, the powers of b go up by 1. And the two powers always add up. N. Thank you. N. Very good. 2 plus 3x to the power of 4. Expand that whole thing out would be 4c0, powers of 2 start at 4, plus 4c1, powers of 2 go down by 1. Powers of 3x go up by 1. 2 powers add up to be 4. 4c2, powers of 2 go down by 1. Powers of 3x go up by 1. 2 powers equals 2. And you get the pattern. And we finish at 3x to the power of 4. And that all tidies up to be that beautiful expression there. Look at that, 216, 216. That's nice. 696. Look, they all end in 6. Except the 81, just ignore it. Okay. Now, some relationships in Pascal's triangle then. NCK will always equal n minus 1 ck minus 1 plus n minus 1 ck. That's basically saying, when you build Pascal's triangle, to get the number, you add the two numbers above it. So to get the number in the nth row, you go to the n minus 1, so the row above it, and then add the 2 immediately above it, which would be the k minus 1 and the kth.
So in like a test, we have to prove that formula, or can we prove it?
If they asked you to prove it, then you'd bring it back to factorials and do it that way. But otherwise, yeah, you can just quote it. Here is a proof, though, not using factorials. I've just gone, okay, well, 1 plus x to the power of n would be 1 plus x to the power of n minus 1. So I've expanded out the 1 plus x to the n minus 1. And then what I'm saying is, well, I just want to find the coefficient of x to the power of k. So on the left-hand side, well, it's just nck, x to the power of k. On the right-hand side, I'd match up the 1 with the term that has x to the power of k in it. I'd match up the x with the one that has x to the power of k minus 1 in it. And so on the right-hand side, it's 1 times n minus 1 ck minus 1. And so that one comes out quite quickly. You don't actually have to go back to factorial to do it. So you could use that idea. Ta-da! Okay, second one. This is the one that's, well, as I've written there, is saying Pascal's triangle is symmetric. So nck will always equal ncn minus k. So the one at the start 1 at the end. First one in, first one in, first one in. It has symmetry about it. If you think of our notation for combinatorics, remember NCK was n factorial on k factorial, n minus k factorial. So again, that's another reason why they're equal. This was very trivial, but that's merely saying that every row in Pascal's triangle starts and ends with 1. So NC0 is defined to be 1, and NCN will also be 1. Okay, 5b. That was a very quick one today. Okay.